So you take something like iron and put it in copper, and it shows some kind of moment. Okay. So the first thing we'd like to do is we want to build a model that will try to sort of see whether an added impurity like iron will possess a moment or not. Okay. So this is what we would like to do, and this is the so-called Anderson impurity problem. So this is I don't exactly remember the reference, but it's Fizrev and I believe it's 1961. Okay. All right. So so what do we have? We have a metal which is a sort of a nice simple metal like copper. So the bands are made of S waves, if you like, of the system. So what we will do is we will write a kinetic energy for that. So that's the kinetic energy. And now what do? I add an impurity at the origin. So the impurity is sitting at the origin. The impurity I'm going to model as simply one orbital. So this is the impurity, and it has one orbital here, which is spin degenerate. So there are two possible, there is an up orbital and a down orbital, and that has its own energy, you can say, and that is like a localized orbital on the impurity. So that orbital you can sort of visualize as some some orbital like that. Okay. So I'm going to write that down. So let me just say that its energy is some CD, and then it has this character. Okay. Then what I can do is I can hybridize this orbital with the conduction electron states. So how I'm going to write that hybridization is that an electron from here can hop on to the spatial wave function right at that point. So it would be something like this. This is the amplitude for that. And then what I will do is I will write this in real space now at r equal to 0, where I've added the impurity, and the impurity dies. Right? So this is what we can do. Right? Okay, so we can rewrite this in terms of these k states, this term, and that will turn out to be equal to, this guy will turn out to be equal to gamma divided by some square root n, number of sides of your lattice or something like that. And you will see that the wave function or the state at the position r equal to 0 has equal weights from all k states. So this will just be this. Okay, so this term is exactly same as this. Okay, so this is what we have. Okay, so the first question we would like to see is, suppose I give you this Hamiltonian. What should I do to see whether this has a moment or not? I should do expectation of sigma z on the d orbital. So it's a very nice answer. So let's see. So what I would like to do is I would like to calculate this quantity. This is what I'd like to calculate. Okay. Now we are trying to solve two problems here. One is we want to we just learned something about Grassmann algebra and all this stuff, path integrals and all that. We want to just flex our muscles on that and do one example using that stuff, and we want to see whether we can get a moment or not. Right? So what I'm going to do is, instead of doing the thing in the usual way of doing second quantized operators and so on, and I'm just going to do this using path integrals, like what we did, the formulation we did in the morning, okay, in the afternoon. Okay, so this is the operator we would like to find an expectation value of. Now, can someone tell me what is the correlator or any kind of thing that I can calculate using path integrals that I should look at to find this value? So let me call this as m. So I want to find this value. So what should I look at? Single particle Green's function. Okay. So what is that object? So let me just write this. I should look at this quantity. That's what people want me to do. Okay. So if I calculate this quantity, how can I get this? Okay, it's not very difficult for you to see. This quantity is equal to sum over sigma times g d sigma of 0 minus. That's what it is. Right? So what do I need to do? I take the upspin chap, take the minus value, so the time ordering will give you d dagger 0, d0, right? That is this guy, minus, so that's where the sigma comes in. For the downspin, you will get a minus sign, and then I get this, okay? And this quantity, you immediately see, is equal to sum over sigma, sigma times sum 1 by beta, g d sigma, I k l e to the I k l 0 plus. That's what that quantity is, if you write it in the Matsubara representation. Okay? So what will be my goal? My goal will be to try and pull this guy off from my calculation using path integrals, and then just do the Matsubara sum. Okay? That's what we're going to do. Okay. Okay, before we do that, I would like to ask you, what are all the symmetries of this Hamiltonian? What all symmetries does a Hamiltonian have? Does it have translation invariance? Okay, there is an impurity, so, and we put the impurity at the origin, so it has no translation invariance. What symmetry, what important symmetry does it have? Okay, particle load we may or may not want to have, that we can put, but any other important symmetry? Okay, time reversal is there, okay. Spin rotation invariance, right? It has also spin rotation invariance, right? So you can choose your z-axis in any which way, and it's the same thing, okay? Yeah. Okay, so what I would like to see is whether within this picture I can find a moment. If I find a moment, I will certainly break time reversal. I will certainly break spin rotation invariance and time reversal. Okay. All right. Okay. Let's see. Okay. So what is the action for this? So I need to write this. I need to write the partition function of this as a path integral. So I will have. I will now use. I will not introduce phi and psi and all that. Whenever I use c, it will mean Grassmann variables in the path integral. I will use d for the. Right, I don't need to use separate psi and phi and all that. Okay, all right. So let me see if that's what I've done in my notes so that you don't get confused. And more importantly, I don't get confused. Okay, all right. Okay, so that's what I've done. And then d star d. And here's the classical action that I need to write. So S is equal to, by now you should be able to do this in your head. Okay, so that's the action. Okay, everybody's comfortable with this? Good. Okay, So now what I'm going to do is I'm going to introduce this action, I'm going to write it in the frequency domain, okay, because it turns out to be easier to play that game, okay. So what I'm going to do is I'm going to introduce frequency variables, and remember that I have to choose the frequency variables correctly because of this constraint that I have. I have these constraints, and the same thing will appear for D as well, okay. So the natural thing to do now is to use the frequency variables as the Fermi Matsubara frequencies, because they have this property that e to the I times kl times beta is minus 1. So if I expand this in the Fermi Matsubara frequencies, this condition is automatically satisfied, okay. So what I'm going to do is I'm going to write Ck sigma of tau is equal to, this is a convention to put 1 by square root beta and so on. You don't have to do this, but it's convenient. Okay, sum ikl e to the minus ikl tau, and then I will write Ck sigma ikl like this. Okay, so this is the expansion. There is a similar expansion for the D. You put all these things in, right, and do the math, and you will find that the action now depends on a set of discrete, infinite set of discrete variables, a discrete infinity of variables, right. And what are those variables? Those variables are C, K sigma, this IKL, and D sigma IKL, and their complex conjugates, etc. And what is that result? You can just do it by yourself. This is sum IKL, right? And then what will I have? I will have sum over K, C star K sigma IKL minus IKL plus Ck sigma IKL. So that's this term. Okay, that's what I will get. Right? You can just see that if I stick this in, I have to use two different IKL and IKL prime here, and when I do that integration, that will give me a delta function on this IKL and IKL prime, and I'll get this. I'll get one of the IKL prime sums go away, and I'll be left with this one IKL sum. That's what I have done. Right? Okay, and then plus D sigma IKL minus IKL plus CD D sigma IKL, and then I of course have that other term gamma by square root n, which is C star K sigma IKL D sigma IKL plus that. Okay. So this is the action in frequency domain. We have simply converted the integrals on time domain to frequency domain, and the path integral now will be written as a set of, you have to just take the integrals over all these quantities. Whatever I have written there. Okay, so this is the story. Okay, any questions at this point? It's clear to everyone? A Jacobian is a constant, so what that does for you is that the free energy gets shifted by some amount. Okay. Yeah. So that's what it will do. Yeah.
K sums and D sums.
There are K sums and
D sums.
I did not understand that what a D sum is.
Okay, that means you are saying it as, that means in the Hamiltonian there was the second term.
The second term, but there's one orbital, that's this okay. Impurity orbital.
It's
so that is
sum. It's a sigma sum.
Oh, the sum over sigma. Okay. Okay. Other questions? Okay. All right. So now what should I do to get the Green's function of the D orbital? Sorry? Integrate over everything else. Okay? That's the correct answer. So how will I integrate over everything else? Okay. So there is a trick, and I will tell you what the trick is. And this is what Antoine in his paper talks about. It can be done exactly. I told you about that. I showed you that line. We will do that. I will show you something that allows you to do this exactly. Okay, and in that we will throw away Jacobians. Okay. Okay. So here is the result. Let's do a little aside. So if you want to think of a physical problem, you can imagine that I have one site here and another site here, and this site has some energy and this site has some other energy, and there is a coupling between these sites. And what I want to do is I want to integrate out one of these sites and find what is the propagator for just this one site. Okay, if you want, you can visualize what I'm doing as that, but I will state it as some Grassmann business. Okay, but it's the same thing. Okay, so here's the result. Okay, so I have two sets of conjugate Grassmann variables, and then I have this object which is e to the a. Okay, what am I doing here? Okay, psi star psi plus b psi star phi plus phi star psi plus d. This time I didn't make the mistake of using c. Okay, all right. But don't confuse this d with that d and so on. Okay, I mean one should have talent, but not that much. Okay, so that's what we want to do. So what we want to do now is we want to do this first integral, right? We want to do the psi integral, so that I get I get this as integral over something only of phi. That's what I want to do. Okay. Everybody's on board as to what is to be done? Okay, so let's do it. So I'm going to expand this guy. Okay, so when I expand this guy, of course the first term is going to be 1, and the second term is going to be a psi star psi plus b psi star phi plus phi star psi plus d phi star phi. Okay, that's the first term. Okay, and the second term is plus 1/2 this thing square, right? Now, I'm not going to write all that down again. What are the important, I'll remove this and tell me what are the things that I need to keep here. Should I keep the square of this? No, because that's already 0, right? Should I keep the square of this? No. Should I keep the square of this? I need to keep only the cross term. And then I need to keep these cross terms as well. I don't need to worry about the cross terms of this because they will also die. Okay? So the only thing I need to do is the cross terms of this and the cross terms of this. That's all. And the cross terms of this will come with a factor of 2, so that will die. Right? And the cross terms of this will also come with a factor of 2, that will also die. Okay? So what will you be left with? You will be left with AD, right? I will write it in this order, psi star psi, phi star phi, correct? And then I will be left with minus b square psi star psi, phi star phi. Okay, why do I get this minus sign? I get this minus sign because there is an ordering difference in the terms. Okay, and that's what will give me the minus sign. You can check this yourself. Okay. Now suppose I do the integration, suppose I do this full integration, what will survive? Will the one survive? One will not survive. What about this term, will it survive? No, because there is the other integral. So the important thing is, when you do Grassmann integration, all the integrands, if I have a multiple integral, every integrand, every one of these guys, every integration variable must appear once, otherwise the term will be 0. If any one of them doesn't appear, it's 0. That's the secret. That's it. That's the exact part. Okay, and then if you just remember this, you can just pull this off. Okay. So now what happens? I don't need to worry about this, I don't need to worry about this, I don't need to worry about this. So what do I need to worry about? I need to worry about this for sure, right? So when I do this integral, I will just get 1. I'm now doing the psi star integral. I'll get 1. So what will I get? I will get integral d phi star d phi, and I will get a 1 here. Sorry. I'll get a 1 here. So I will be left with AD times phi star phi like this. Good? Okay. And then I'm left with the same thing. I'll get minus b square phi star phi. Okay, everybody good? Okay. Now what I'm going to do, just for keeping books correctly, I'm going to take a factor out of here, and the factor I'm going to take out is minus a. That's what I'm going to take out. So what am I left with? I'll have a d, and I'm going to open my, I will open a bracket here, and write a here, and close the bracket. Does that work? Okay? Okay. Now, if I imagine this to be a partition function of something, I'm multiplying something by a. So this is a shift of free energy, which I can throw away. Right? So I don't need to worry about this. This multiplication I don't need to worry about. It is there, it shifts, but we don't care. Okay? So what am I left with? I'm left with this. Okay. Now what you do, you just open this bracket out a little bit, and put the bracket out here, and just put a 1 here, because that's, you can add 0 to the partition function. Right? 1 minus this, because the integral over d phi phi star of 1 is 0. I'm certainly allowed to add 0 to a partition function. So what have I just found? I found that the effective integral of this guy is, let me just write down here, that result is the following. Sorry, I should have d what is this? Phi star phi. Okay. So do you see what this object is? Do you see the result of the, do you see what that object is in result to the previous talk? No? See, this is the B is the coupling, right? And this is the energy denominator. A is the energy denominator. So it's like T square over U, right? It's exactly that. So if I want to integrate out this state, say I have these two states, they are coupled. I want to integrate out this state. So what should I do? So I want to be at this state, but there are quantum fluctuations going there and coming back, right? So when I go there, I propagate with the propagator of that state. So it'll pick up some stuff which is inverse of that, right? A is, remember, the inverse propagator of A. A is inverse propagator of the state phi. So I will propagate a little bit. So I have to put inverse of inverse propagator, which is 1 by A. So the hopping amplitude to that is B, and I propagate there for a little while, and then I come back. So that adds self energy for me for this state. That's the physics. So you could have written this down without doing all this calculation. But then that may not be exact. But this is exact. Okay? You got the idea? You got the idea of what is happening? Yeah. Okay. Now what you have to do here is, you have to do this k by k. There are many, many k's, right? You have to do this k by k. So this psi here phi was my like D state, and the psi was one of the ck states. Suppose you do this k by k, what will happen is that the additional piece that I'm getting, many, many things will get added onto that. Because from this state I can hop onto many different states, and I can propagate in many different states and come back. So my effective propagator will pick up additional self energy terms by, because I'm hybridizing with various possible states. Okay. So if you do all these calculations, which you can do, it's all just playing with Grassmann numbers, not very difficult. What you will end up getting is, let me erase some of the stuff on the board. What you will end up getting is this very nice result, which is that the action only in terms of D is the following thing. Right? Okay. So I'll certainly have this D star sigma IKL here, right? And then I will have this, and this D that I have, that is simply the propagator of the D state itself, right? So that will be minus IKL plus CD, that term, that is D. And now it couples with the other guy, with all other guys. So let me just write it for one particular K. So the coupling is gamma by square root n multiplied by gamma by square root n. That is the B, this thing, B square. And A is the propagator of that particular K state, the inverse propagator of that particular K state, which we will write it like this. Right, this is for one K state. I need to do it for all K states, one by one, which you can do. And what will I end up getting? I'll just end up getting this thing here, like this. Is that good? Yeah, D sigma IK. Okay, so I have just pulled off the Green's function of the D state, G D sigma of IKL is equal to, remember the convention thing is to write this with a minus sign, right? So I need to get the minus signs correctly. So this is inverse IKL minus CD plus sum K plus 1 by n, right? I should write this as gamma square by n, and then sum over K 1 by I need a minus sign on this. Minus sign, right? IKL minus CK. Okay, this is what it is. Okay, everybody's good? Okay, now I can rewrite the impurity or this action for the impurity back in time domain, which is what you saw in Antoine's paper the first day I showed you, right? And what is that? That would be integral 0 to beta d tau, integral 0 to beta d tau prime, d star sigma tau, and then I would have minus g sigma sigma prime tau minus tau prime, right? And then I would have d sigma tau prime. This is what it is. And what is this g sigma sigma prime tau minus tau prime? It is this quantity, you take it, Fourier transform it, right? You take this quantity, Fourier transform it, and put a delta sigma sigma prime, because in the way we have done things here, or in the way we have set things up, when the impurity hops into the conduction band, it does not change its spin. So the spin is never changed. Okay? So what this thing, G inverse sigma sigma prime of tau minus tau prime, is just the Fourier transform of G inverse IKL that I found, multiplied by delta sigma sigma. Okay, this is what you saw in the first day I showed you. Okay, so that's the formulation part. Now we'll go to the physics part. Okay, any questions at this point? It's late in the day. Okay, it's clear, I suppose. Okay, all right. So let me do this calculation now. Okay, so first, before I do that calculation, I want to see what this result actually means, this result, right? So let me go to the real frequency. The real frequency, if I analytically continue this to real frequencies, I will get the Fourier transform of the retarded Green's function of the impurity site, right? And if I take the imaginary part of it, I will see what is the spectral function of the impurity, right? That's what I want to do. Okay, so let's do that. So I have G of IKL, so that's the inverse of that thing. Okay, that's the inverse of that. Okay, can someone do the analytical continuation of this? It is late in the day, I can see that. Okay. So wherever you see IKL, just replace it by omega plus, because we have actually an analytical formula, right? So this is analytical continuation by chalk. Okay. So this becomes omega plus. I don't need, you'll soon see I don't need to worry about the omega plus. Okay, this is omega plus. Okay, very nice. So now I want to find the imaginary part of this quantity with minus 1 by pi and so on. Okay, I need to do that. Okay, so let's see what happens. This is already a complex quantity because there is an omega plus sitting here. So I don't need to worry about this omega plus anymore because I have something complex to handle any problems that I will encounter. Okay, so let's look at what that quantity is. That quantity, gamma square n, is equal to sum over some principal sum over the real part, which is 1 by omega minus ck, right? And then what I need to do is I need to look at the imaginary part. The imaginary part will be minus 1 by n with an I pi sitting, I pi gamma square, 1 by n sum k delta of omega minus ck. Okay. So what is this quantity? Do you know? That's the density of states, right? That's the density of states of your conduction system. Okay. So this quantity is the density of states. Okay. So now what we need to do is we need to actually have some model for the density of states so that we can do some calculations. Otherwise we will be just having formulae, right? So let's have a model for the density of states. So usually the density of states of these systems is more or less flat. So the standard model that people would choose would be something like this. It's a flat band with width going from minus w by 2 to w by 2. And that will tell you what the density of states is, because the integral of the density of states has to be 1. Right? That's a sum rule which we have seen. So this quantity, which I will call rho naught, is actually just 1 by w. It would depend on underlying ladder, sure. So if you want to do some very complicated density of states, please be my guest. Right? I mean, this is hard enough for me. Right? But for D band metals, you know, so metals in the transition series, right? This is not a bad approximation. Yeah. Okay? All right. Okay, so that's what happens. And now I have this real term, right? So actually the real term requires a little bit more work, okay? And somebody was talking about counter terms and all that stuff. So if this thing were not a finite band and so on, then this will actually blow up to infinity and so on, and then you have to choose CD to have some counter term, cancel it and all that stuff. Okay, so we don't have those problems here because it is a finite band. But nevertheless, there is some number you have to extract out of this. So what I'm going to do is I'm going to assume that all has been done, right? And I'm simply going to absorb that into the definition of CD. Right? You can see that I'm getting more and more sort of physicsy now. Right? Okay. All right. So let's do that. So you may wonder, you know, oh, this real term is frequency dependent and so on. Yes, it's frequency dependent, so you have to find some pole of this, and there's some work to be done, but let's not waste time on that because you know, we want to chase physics, and somebody else has done these things before us, so we just use it. Okay, so what you see after all the dust has settled, so what is this delta? This delta is equal to, just look at here, it is just pi gamma square times rho 0. Rho 0 is what I have defined as 1 by width. Okay, that's what it is. Okay, I think I've got it wrong. It will be that. It's very important that it is that. Okay, so what have we found? What have we found? What is the meaning of that equation? Huh? Okay, so this, okay, so first let's discuss the mathematics. So this has some pole in the lower half plane. Okay, that's already very good. Huh? Now, what does it signify? So what that signifies is you need to look at what is this in time domain. If you Fourier transform this in time domain, what you will get is, I'll just do that here in the side. If I do g sigma of t like this, you know this will Fourier transform to some theta function. So let's put all that. So this will be theta of t, and then it will become e to the minus I, this quantity, right? CD minus I delta t. So what is the meaning of this? If I create a particle in that state, over a period of time it will decay, right? So what that means is that this forms what is called as a quasi-bound state. It's not, if it were there forever, then it's a bound state. It's stuck to that. But now what you get is you get a quasi-bound state. Okay, now somebody was asking me, why would you get some, self-energy, have imaginary part and so on? So somebody was asking me, yeah. So now you see the imaginary part can handle stuff like this, right? So you can get, if I have a quasi-bound state, then it has some things and so on. Okay, now I would also like to make a connection to the previous talk, right? So in the previous talk, what was discussed was something called the spectral function of some cuprates. So there what was done was you actually looked at this quantity with k as the momentum label. Right? So what was looked at was something like this with momentum label like this. And what was found there is that, okay, I will first plot, sorry, I'll come back to this in a minute. Let me now look at the spectral function. So this is a d sigma of omega, and I need to look at the imaginary part of this for the spectral function. So this is 1 by pi g d sigma of omega plus. And if I do that, what I will find is, I will find that this quantity is 1 by pi. And what do I get? I get delta divided by omega minus CD square plus delta square. This is what I will find. Okay? And if you make a plot of this, which I should do well because I will need it later. Okay, so what I will find is I will find this is the omega axis, this is 0 of my energy. Let me assume that CD is negative, so my CD is here. What will I find? I will find something like a Lorentzian, something like this. This is what I will find. Okay, Lorentzian is supposed to be symmetric. Okay, just use your imagination and make this symmetric. Okay, it's not terribly symmetric, but okay. Okay, that's what I'll find. And this width will be what? Yeah. Okay, so you can see that. Okay, that's the result. So it has a finite lifetime, and the lifetime is sort of inverse of this width, right? So you can see that if gamma were 0, for example, it doesn't hybridize, then delta would be 0, and then it will be a fully bound state, in the sense that it never pops in and out of the conduction band. Okay, all right. So now if I have something like this, and the quantum number were k, like what was discussed in the last talk, and if I find that the spectral function like this was, looked something like this, and then it had the sharp peak like a Lorentzian, and then what I would say is that there is a quasi-particle in the system. And this kind of Lorentzian, a single Lorentzian peak and some background feature, smooth feature, the single Lorentzian peak will then indicate that you have quasi-particle-like excitations in system. And what happens in cuprates, as you saw in the last talk, is that in some regimes, you just don't get any such thing. You get two peaks, you get all kinds of complicated things. Okay? So you don't have good quasi-particles. Okay? And then once you don't have good quasi-particles, your usual ways of thinking about transport, for example, you would like to think in terms of some Boltzmann transport equation, write some kind of semi-classical equations for motion of these quasi-particles, and then you can model how transport takes place, and so on. Those things break down. Okay? And we saw, for example, the resistivity is just going without no end and without any end, just going up and so on. So you'll see some strange features if this thing breaks down. Okay, so that's the connection to other things that are going on in the school. But okay, so let me come back to our Anderson impurity problem. So what we have found is that the impurity lives on the D state, the electron at the impurity lives at the D state only for short or long, depends on what is delta. It lives there only for some finite time, it just hops in and out, right? So stuff gets in there, stuff gets out of there, and so on, right? That's the picture. Okay, any questions on this? Not in any serious way, right? So for example, if the density of states had some so suppose your CD were like this, and if this is CD and if your density of state went 0 there and all, then some changes may take place, right? But if it doesn't, if your density of states is roughly featureless, then it's okay. Yeah. So the answer to the question is, for starters, no. Okay, other questions? So this was precisely the question the gentleman at the back asked, like, what happens if I have a real band structure and so on. Okay. Okay. I proceed. Okay. All right. Now what is our next goal? We want to do this calculation, right? So we have all the analytical results here. I have the G, I, K, L and so on, right? Now I will just assert something which you can prove yourself, okay? And the assertion I have is the following: 1 by beta sum over IKL G K sigma or G D sigma of IKL e to the IKL 0 plus is equal to integral minus infinity to infinity d omega nf of omega Fermi function a d sigma of omega. So you can prove this. Okay. So proving this is called as the Matsubara summation, and so this 0 plus comes because we want this at 0 minus for the Green's function, and that actually helps you converge the integral and so on. And well, I will not get into the technicalities of this, but it's found in any textbook actually. Okay. So this quantity is actually equal to expectation value of d sigma d sigma. That's what I have calculated. Okay. Okay. All right. Can you tell me what would be the answer for this? I have this at t equal to 0. Suppose I were to do this calculation at t equal to 0. What would be the answer for this? The answer for this is actually pretty simple. You take this object will be a step function up until this point. So what happens is, quote unquote, all these states, all these energies are occupied. So you need to do the integral up to this of the Lorentzian. Okay? And it turns out that's not very difficult to do, particularly if you have Mathematica. Okay? So this quantity is 1/2 minus tan inverse, I suppose I need a pi or something there, I'll find out, by delta. I suppose I need a pi, 1 by pi or something. Yeah, I need a 1 by pi, yeah. Okay, so this is the result. Okay, so there will be so much of occupancy of this impurity state, it will not be 1, and why is it, so for example, if you can see when CD is negative, this tan inverse will give you some, if CD is positive, for example, if CD is positive means if this is the chemical potential, you are here. So then, you get a little bit, if the CD were here, you will just get a little bit of stuff, the spectral function has something getting into the inside the Fermi's energy, that part will get occupied. So that will be small. But if CD is negative, if CD is here, then what happens is this quantity is negative, and I'll add on to the half. But the whole impurity state will not be occupied because of this leaking into the conduction band. Okay, that's the physics. Okay, so now tell me, what is the magnetization? Oh, sorry, this is up. So what's the magnetization? 0. Hey, but that's too bad, no? We did all this work to find a 0. Perhaps that's familiar to a lot of us, but this is terrible. So what do we do now? So all this Grassmann stuff, was it worth it? Really? You're supposed to get some answer, right? At least you should find some condition under which, so how many parameters are there? Okay, let's develop that idea. Okay, so how many parameters are there in the theory? There is CD and there is delta. The answer depends only on those, and it depends only on the dimensional ratio of those. Right? So you have these two parameters and you can pull off one dimensional ratio of that. So actually there's only one parameter. So we cannot do anything to get a non-zero answer. Whatever is this parameter, you'll get 0 as the answer. So what should we do? No, my friend. See, this answer does not depend on sigma. For up and down spins is the same thing. See, I'm just cheating you, right? Because actually these are two copies of the same Hamiltonian with different spin indices. So they are actually the same thing. I have to add another term. What term do you want to add? Interaction. Where? No, you wait. I think you should wait. Yeah. No, experts should, yeah. What interaction? Impurity on-site interaction. So okay, where is this is the first quantized version. Let's not get confused by Grassmann variables and all. Let's just talk simple physics. What should I do here? What do you mean by impurity on-site interaction? Okay, you want to put a U? Let me put a U. So let me get rid of this. I'm going to write. This is a suggestion from the class. So what should I do? I should add something. Now what should I add? Okay, U times, I will write it, since, see, I want to be purist, so I will write it in normal ordered form. You want to do this. This is what you want to do. So why do you think that this will give you a moment? You will, if there's already an electron there, it will oppose the incoming electron. That's a good idea, right? But I will show you explicitly that you will actually promote a spin to form, and it's very easy to see. So what I want to show you is that a term like this already suggests to you that there will be some kind of spin wanting to form at that site. Okay, and it's actually some very simple algebra that we have to do. I just need to find a good place to do it. Okay. All right. Okay. Now, before I proceed, I just will add I just will finish the formulation part so that when you hear Antoine's talk, etc., you will not be lost. So suppose I were to put this U in the problem. What will be the action now, or the impurity action? I just put this U, and you can do all the integrations, etc. The impurity action would be something like this. It would be integral 0 to beta d tau, integral 0 to beta d tau prime, d star sigma tau. There will be a minus G inverse sigma sigma prime tau minus tau prime, which I have already derived there before, d sigma tau, right? And then I'll have this impurity term, the interaction term, which I just add on to this. Right? So you see, so there was, I had showed you two panels in the first meeting. right? I wrote the Hubbard model, and then there was whole set of stuff done, and then it was stated that it can be exactly shown that the action will become this. So you see, that's exactly the action that was written there, right? So this is an impurity with an interaction. So this is the action for that. Okay. So now I have redeemed my second promise. Right now the third one is I have to show you whether moments form or not. Okay. Yeah.
So if you exchange up and down,
where?
On the U.
Yeah. It will be the same operator.
Oh.
Sorry. So that comes from spin rotation variance and all. We can see this. So this apparently breaks spin rotation variance, right? Because I have chosen some up and down direction. Just give me a minute. I'll sort that out for you. Yeah. No. If I had only this, then I have to calculate the impurity susceptibility, and that need not. Why should that be temperature dependent for? That will sort of depend on if the it will depend on what is this object. You understand? There is no reason for it to become temperature dependent. It certainly need not be 1 by T. Yeah, there's a question at the end.
Instead of introducing U, for example, if I take a coupling to be a spin dependent, for example, gamma sigma, will it help anything?
It could help, but it breaks some symmetry. It may or may not break a symmetry, depends on how you couple. Yeah. Yeah. So for example, what you're saying is right. Okay, just wait. I mean, I will actually do what you're saying. We'll start here and get to something called the SD model, which is what will happen. Yeah. Okay. Other questions? Okay. Proceed. Good. Okay. So this is so I suppose much of the technical stuff is done. So from now onwards, I'm going to switch to more physicsy things. So I will be making approximations and this and that. I will not be very exact and so on, but I'll try to give you the flavor of the physics that's at hand. Okay. So now let's take this guy and let's work with it a little bit. Okay. So this as an operator can of course be written. Just look at this operator. That can, as was suggested, can be written as ND up, ND down. There is no. I'm not doing anything wrong there. Okay. Now you can show this very, very beautiful result, which is the following. I'm looking at my notes because I want to get the factors right. So if there's a mistake, it means that when I was working it out, I've made a mistake. Okay. So I may have made a mistake. Okay. So what I can show is that ND up, ND down, which I've already written down there, that is equal to 1/2 N up plus N down minus 2/3 SD dot SD. Okay. What is this object? Yeah, you remember this? Okay. Okay. All right. So now let's see whether we'll get a moment in some limit. Without doing any calculation, let's see whether we'll get a moment in some limit. Okay. So what you do, choose CD to be negative. So the impurity state is below the chemical potential. So you can occupy that state at 0 temperature, say. Okay. And now what you do is you take U to be very large quantity or whatever. Then what will happen is, if I have both the sides occupied, I mean if I have both up and down spins occupied, then this term will be 0 because it will be a singlet. Correct? So this S operator can be either a singlet or a doublet, like a spin half. Right? Singlet when I have both these up and down occupied at the D side, doublet if I just, if I have only singly occupied. Right? So what will it favor at large U? Right? At large U, you can see that it will favor this. Right? And then you can immediately see that I will get a moment. Why? Because it will maximize this spin energy that we have seen. So what will I get? My ground state at gamma equal to 0 will be the filled Fermi sea of the conduction band and one particular electron sitting at the d site, and its spin can be anything, right? So now you immediately see if it didn't couple at all and if I had a very large U at a site, I will get paramagnetism. I will get this Curie 1 by T behavior. Free moment will be there, which will couple to a magnetic field in the usual way, and I will get this. Sorry. But 2 by 3 is, So this is the origin of, and this is precisely the physics by which in the Hubbard model, which you saw in the last talk, also you get spins at a site. And in Hubbard model, you also get some additional physics, which is a formula which will also show up here. We will show you. Is that I have spins on this side, I have spins on this side. So in the u equal to infinity limit, in the most strongly correlated limit, right? And you just keep half filling, so each site has one electron. The remaining degree of freedom is only spin degree of freedom. It's completely degenerate. It cannot talk to any other spin. But if I don't have u equal to infinity, but if I have u equal to some large value, then I can get a new scale in the problem by precisely that virtual process. So what can happen is that the electron can try to gain kinetic energy by a virtual process. So the virtual process, I have these two sites. So if this is upspin and this is upspin, I cannot do any hop. So I can never gain kinetic energy by hopping. But on the other hand, if this were downspin, I can do a hop, but that state has energy u, but I come back, right? So I will get, so the triplet state and the singlet state that you will get out of this will have different energies because of this virtual hopping, and that gives you a spin-spin interaction. So the emergent degrees of freedom are spins at every site. No charge is gone out of the picture. You get spins at every site as the degrees of freedom. And the new low energy Hamiltonian for those spins is this JSI dot Sj, which is the Heisenberg model. So you can speak out you can just talk your way out, starting from the Hubbard model at large U limit, how you get the Heisenberg model. Same thing, no? This is minus sign. So if you just calculate out the energies, if I have a singlet, this would be 0. If both are occupied, it will be 0. And so the same reason why you get moment in the Hubbard model. Charge fluctuations cannot take place. So spin is the degree of freedom. Okay? So you already see that u has to have something to do with this. Okay, all right. So now what we would like to do is, we would like to see what is the moment and how there is a puzzle actually. You should ask me a question. So I said that at high temperatures you see this moment, but at low temperature the moment seems to go away, right? You get a finite susceptibility. You don't get a divergent 1 by T divergent susceptibility. You go to some finite susceptibility. So the moment somehow gets quenched. So how does that happen? Sorry? Singlet? Somebody said singlet? No, who is speaking? Singlet with what? Okay, so you know stuff. Okay. So, okay. Okay, so let me just now try to develop a theory including the interaction. Okay, so what I'm going to do is I'm going to play some, I'm going to make a lot of simplifying steps forward. The first thing to do is, you see I have this ND up, ND down here. That will show up in this term, like this. First thing I'm going to do is, I'm going to take the U times this ND up and absorb that into CD. So I don't have this one body term remaining. It's absorbed into CD. Good? Okay. So there is a nuke CD in the problem. Okay. So that nuke CD has been defined. So my effective Hamiltonian now is just this. D and U will be here, SD dot SD, like this. Okay, I'm simply going to write that. So CD has now absorbed that thing. Okay? And I'm also going to work in a nice limit. I'm going to choose my parameters in such a way that there is some nice symmetry to this. And the symmetry is the following. Okay? So this is the chemical potential. And this level is the nuke CD. This is 0 chemical potential. Okay? So this thing is CD. So if I occupy a state here, that will be CD. What happens if I put 2 electrons? So suppose I put 2 electrons. The state will go up by CD plus U, actually 2 CD plus U. That will be the state. And so what I want to do is that I'll get a state here, and I want to keep this perfectly symmetric. Right? And that will happen if I choose CD is equal to 1/2 U, like this. Okay? This is called as the symmetric Anderson model. Okay? It just simplifies life a lot. So let's just do that. Okay? All right. You can of course relax these things and do it as a homework problem. Okay. So now what is my action? I have this, and instead of writing it in the way that you will find in Antoine's paper, etc., what I will do is I will write it using the spin language. Okay? So what is my action? So Indra, you have to tell me when to stop. Oh, okay. So no, but there are people who may get violent and so on. Yeah. Okay. So okay, we will try. Okay. Yeah. Okay. Yeah. So anyone has any objection, just let me know in advance, and I will stop. So you don't have to take any drastic measures. Okay. All right. Okay. So integral 0 to beta d tau, integral 0 to beta d tau prime, and then this is minus G inverse. Okay, there is a d sigma. Okay. There's a d star sigma tau minus G inverse sigma sigma prime tau minus tau prime, and then there is a d sigma tau, and then I have this the usual 2/3u integral 0 to beta d tau sd tau dot sd tau. Okay, I have this. This is what I have. Okay. Now the question is, I want to do at least start analyzing this problem. It's not an easy problem to analyze, believe me. Okay, but I want to start by developing some techniques for analysis. Okay. So one technique for analysis, which is what we will call as a saddle point technique. Okay, it's called the saddle point method, and let us see whether we can see the formation of a moment within the saddle point method. Okay, I will need to hold on to that picture. Let me just. Okay, so the main trick of the saddle point method is the following identity. Suppose I had a set of numbers e to the b star b divided by some number a. Okay, what is this b? This b can be a complex number or a product of two Grassmann numbers. A product of two Grassmann numbers is like a complex number in terms of algebra. You can move it around and so on. It commutes, right? So this b can be either a complex number or a product of two Grassmann numbers. In fact, it can be a product of any even number of Grassmann numbers. Okay? This quantity is equal to, can you guess? Okay. So it's is equal to dz star dz e to the minus a z star z minus b star z minus z star b. Okay, there are some factors. We don't need to worry about factors because they'll be multiplicative and they shift free energy. We don't worry about those. Okay, so what is this identity? Oh, okay. All right. So you know, okay. No, it's Hubbard. No, we should give credit to Hubbard and Stratonovich. It's okay. Right. But what is this identity? By that question I meant, how do you see this identity? It's nothing. It's just completing the square. Right. So what you do, you just complete the square, and then you just do these integrals. So you'll get some constant multiplied by this quantity. The constant is the integral of this. It's just Gaussian integration with shifted Gaussian integrals, right? So z is shifted by some b and so on, right? So you just complete the square and do the integral. So this is the result. And this thing has a fancy name, which is what was mentioned. It's Hubbard-Stratonovich transformation. I don't know whether it's an A or O. Okay, everybody's good? Okay. All right, that's all we need actually. Okay, so now let me just take this action and write the action out. So the partition function is this. I have this d star d, etc. And then I have this this impurity, the free action. So let me just call that S naught. You know what I mean? It's just this guy, right? This guy. And then I have this minus 2 by 3 u integral 0 to beta d tau sd tau sd. I have this. Okay. So now let's try to understand what I'm doing. So if you want to imagine, this can be thought of as that there is some kind of glue sticking the spin operator with itself. Right? So this is like interaction of spin with itself. S dot S. So there's some kind of glue that's sticking these two guys together. Right? So what I'm doing is, I'm taking this object and I'm just stretching that guy out. So you'll see the glue now. Right? That's exactly what's going on here. Right? So this is stuck by a glue, and I'm undoing that glue. That glue is Z. Right? So what do I see? I see the B and B star. Stretch it out. That's the Hubbard-Stratonovich transformation. So if I have some quadratic operator, you can visualize that they are stuck by something, and you can unstick them. But when you unstick them, you see, if you have broken an eclairs or something, you'll see, right? That stuff is the Hubbard-Stratonovich field. Right. Okay. So let me do that. So what do I need to do? I use exactly this result, and let me skip the algebra because it'll just get a little painful. And let me lift from my notes. It's not terribly painful, but I have to say that I'm not feeling super energetic after so many hours. Okay. All right. So this is what happens. I get an additional field, and there'll be a field M. Now you see, this is a vector operator. So my Hubbard-Stratonovich field will also be a vector field. Right? It has to, because my action has to be a scalar. Okay. So what will I get? I will get e to the minus s naught. Okay. Now if I use all that stuff, I will get plus 3u by 2, I suppose. Something, there is an integral 0 to tau, of course. M tau dot M tau. This is my Hubbard-Stratonovich field. And then I will have minus M tau dot SD tau minus, okay, I can just put some 2 or something. I can just put a 2 then, because these are real fields. I may or may not need that 2, but it really doesn't matter at the level of my discussion. This is what I get. This integral is 0 to beta, of course. Thank you, Odip. Okay, so that's what it is. Okay, now view this problem from the point of view of fermions. What happens? This original problem was a problem in which the fermions were interacting with, the d fermions were interacting with each other. There was a spin dot spin term. Okay, now what have I got? I have got a new system in which there is a new field called this Hubbard-Stratonovich field, right? But the fermions are no longer interacting. Why? Because this is a quadratic operator, but what I have now is a time dependent field and the dynamics of that field, that is this quantity, right? So what I have done is, I have taken this, there was something binding these two spins, that's this term that I had, and I undid it. So when I undo that, the fermion now sees only this thing that is binding, that is this M, and that's a time dependent potential, right? Right? You get the idea? Okay. So what I can do is, I can absorb this thing, this object, into the definition of S0. No? Some people are looking a little, because this is a real operator. Yeah. You can keep, if you want, you can take it imaginary, it's all fine. It'll all, anyway, the saddle point I will use is real. So for example, Sudeep, if I did this in the pairing channel, then I will not keep M as real, right? Because that is, yeah. Yeah, please. SD is quadratic in fermionic. That's exactly right. That's exactly what I'm saying. Right. So we have two things now. I have traded in my interacting system. I have traded in for my a quartic interaction. I have got an additional field to worry about, which is this M. But I have my fermions are now quadratic. Yeah, everybody is good? Okay. All right. So what I'm going to do is, I'm going to just formally write this. Okay. So this will be some. I will just write it like this now. D of d sigma tau minus tau prime, and then I will put formally that it depends functionally on M, right? Because there is a potential that has to be added to this propagator now, and that is this M, and then just write this as d tau prime like this. Okay, that's what happens. And then I have the dynamics of this other field, which is integral 0 to beta. And then this is M tau dot M tau multiplied by the inverse of U. Actually, it will be some 1 by U. Where did I get that? Yeah. 1 by 2U. Okay. So this is the result. Everybody is good? More or less fine? Okay. Now you see, this object looks like a generalization of a simple formula that we had derived. What is the simple formula that we had derived? We derived this formula, integral d phi star d phi e to the minus a phi star phi is equal to a. Correct? So suppose you were to sort of think of this object. This is a big matrix. This is a matrix with tau prime labels, sigma prime labels. So this is a matrix with continuous entries and two discrete spin labels. So suppose I were to generalize this to matrix. So what will I do? Okay, some of you may not be able to see, but okay, just assume that this is transparent for a minute. Okay, right? So let me just generalize this, phi star d phi I e to the minus, let me just say some aij, right, some phi star I phi j. Okay? Suppose I have something like this. What will this integral be? Determinant of A, right? Excellent. So you can sort of, if you want a cheap proof of it, you can do some unitary transformation on this guy. Then this fellow will break up into different guys, and okay. All right. So this is actually much more generally true. You don't need this to be unitary and all, but let me not get into all that. So this will be det A. Okay. So now what can I do? I can actually integrate out the fermions completely. So what I will get is an action only for this glue field, the M field, right? So I can integrate out the fermions by that, and what will I get? When I integrate out the fermions, I'll simply get the determinant of this matrix, this G matrix, which has functional dependence on M, right? So if you do that, what you will get is you will get integral d m e to the minus integral 0 to beta d tau 3 by 2u m tau dot m tau minus log determinant of minus g inverse tau minus tau prime, g inverse of m. Let me just write it like that. This is what I will get. Now how did I get this log determinant? So when suppose when I do the path integral, I take the path integral on the m at the end, and I do the path integral on the d's, right? Then I'll get this, I'll retain this, that's this term, and then when I do the integral, I'll get determinant of this guy. So I need to lift it up to the numerator. So I put a log, put two minus signs, one here and one here, and I'm done. So what do I have now? I have a classical action of this M field. This is the classical action of the M field, this object. So you see, I started with fermions, I pull them apart, their interactions, and then I integrate out the fermions. Now what am I getting? I'm getting these fields which are binding the fermions to interact with each other, right? And that's that. Okay, great. Now what do I do? Don't tell me stop. No, why would I do something like that? Sorry, to get M? No. But why is it reasonable to do that? No. Why is it reasonable to look for saddle point of this? First of all, what do you mean by saddle point of that? This is the classical action, right? So what do you mean by saddle point of this? It is the one that is the classical solution of this problem, without any quantum fluctuations, so to speak. That is what would be the classically allowed trajectory for that object. Okay, that's what we are looking for. Now, why is it reasonable to look for that? That's my question. Why are you believing that this should be fine? Sorry? No, ground state, but why would you look for the classical solution? Okay, we don't know it's correct, that's fine. So I'm asking, why do you believe that you should do this? Okay, there's one simple reason. Okay, it's late in the day and we all want to go home and eat lunch, so let's do something. Okay, that's a reasonable answer. It's something we can do. But why is it reasonable to generically do this? If you were a perturbation, then we'll not get the strong correlation and all that stuff. Right? No, that's not the line. So yeah, I see what you're getting at, but just hold on to that. That's not the line to go. So the reason for that is, it's probably not a good place to do this. It's not a good place to do Hubbard-Stratonovich transformation and be happy with it. Okay, you will see why. If you do Hubbard-Stratonovich transformation and be happy with it, you will never see the Kondo effect. So this is not, and this is related to your question, right? The one about symmetry breaking. Okay, so this is a finite system, and I'm going to do some classical stuff on two things. It may not be the best thing to do, and this you have to have some experience to see that it may not be the best thing to do. But if I were doing a magnet, for example, say for example I have Hubbard model at some quarter filling or some small filling, right? And if I want to see whether it has a ferromagnetic state, this may be a reasonable thing to do, right? And why is it a reasonable thing to do? You see, what I'm going to do is I'm going to find saddle point equations of this, and in calculating the saddle points, there may be many saddle points. But I'm going to calculate some simple saddle point which I think will match experiment or which is motivated by some physical intuition or something. So the typical one I will choose is that this m will be independent of tau. It will be just a constant. That's like a magnetization of the system. So if it has a magnetization of the system, it breaks the symmetry, right? And then it picks up an order parameter. Now, why is something able to hold on to a broken symmetry state? Because this order parameter, this big object that has come up, is so huge that its fluctuations are very slow, very classical, right? They're heavy in some sense. So it's reasonable if I have some big system and it breaks some symmetry to believe that this mixing is going to be very slow, and therefore I can do Hubbard-Stratonovich and believe that it could be the correct answer. But there is no a priori reason for me to believe that the Hubbard-Stratonovich will be the correct answer here. Sorry, that last statement was completely wrongly stated. It's to do saddle point analysis. Hubbard-Stratonovich is exact. I'm terribly sorry. I misspoke. There is no reason to believe that if I do saddle point analysis for this one impurity problem, that I will get the correct answer. But if, for example, if I had like Hubbard model at some small filling, and if I want to see some kind of Stoner instability of that, see some magnetization show up, this would be a very reasonable thing to do. In fact, you can take this program through exactly in the same way that I've written here for that purpose. Because I want to see a symmetry broken state. So I want to see a moment form, right? So that moment is something permanent, right? So that's the idea. You can try to find other saddle point solutions, okay, but that's hard. Okay. So shall I then proceed? Yeah. Okay. So that's okay. M will be like, that's a great question actually. So if in this way of viewing it, right? What is this M? M is like an external magnetic field on this guy, right? So who is providing that external magnetic field? Not the other. In this case, the same spin, right? So how can the same spin provide a magnetic field? Because then it picks up a magnetization. So it self-generates the symmetry breaking field. Okay, that's the idea. The answer to your question is the idea of spontaneous symmetry breaking. That external field or magnetization. So magnetization divided by U or something will be this field. That is self-generated by the system, spontaneous symmetry breaking, right? That's the idea, right? Okay, we are more or less on board, everyone. Okay. Then the question is
a question. So you said that in the Hubbard model it's valid to do the saddle point solution.
Valid is okay.
No, it can be done, but here it's not possible.
It's
not good to do.
It's not good to do, and I'll show you why. I'll show you why.
But both, if you're saying for the small fillings, Hubbard model can be done. So, but in the single impurity also is like a
okay. So those are things we can discuss. So you're asking some more subtle questions. For the single impurity problem, why it is not, see, it's like this, right? See, if I have a double well potential, you will see the double well potential very soon, right? Then, what is the ground state of a double well potential? It's not that the particle is here or there. It will hybridize, and if you can view the particle to be here, you can view the particle to be here. You will be very good if you are at high temperatures or something. But as you come lower and lower in temperature, these guys will have a quantum tunneling between these guys, and you will get an exponentially small reduction of energy by hybridization of these two guys. That's the Kondo scale. Okay, and that you will completely miss out if you just be happy with this. And okay, I will read out from Anderson's paper what he thought when he did this for the first time. Right? Okay, let me do what he did. Okay. Okay, great. Yeah. So Indra, can I just take 5 minutes and complete what I'm saying, and then I'll take the questions. Yeah, I'll just finish this. Okay. So let me tell you, I'm going to switch to complete. I'm going to switch to English language and graphs. Okay. Okay. So let me very quickly give you the idea of the Anderson impurity problem. So what you would now do is the following. So you take this guy and you assume that m tau is equal to some m times Ez. Right? You assume some direction it's going to point. Okay? And then you do all these calculations with this fixed thing, and it's very easy to do. You can all do it. It's very easy to do that calculation. And then what you do, you plot the free energy of the system or ground state energy of the system, which you already have the partition function. So take log of it, multiplied by t, etc. Do all the usual stuff, right? And then you plot this out. And what you will see is something very beautiful, actually. You will see that you will get a curve for the energy or free energy or something as a function of m to be this, right? To be that, even higher it would be something like this. So what are these three curves for? These three curves are for different values of u. Okay? So this is for a value of u by pi delta, which is the important parameter, right, to be greater than 1. This fellow is u by pi delta to be equal to 1. And this fellow is u by pi delta to be less than 1. This curve was obtained by in a set of 3 papers by Anderson Uval, by Schrieffer, Everson and Wong, and Hanman, 3 side-by-side papers in Physics of Letters in 1969 or something like that, this curve. Okay? So what do you see? You see that for large u, you get 2 states, the up or down, m equal to plus or minus 1, some plus or minus some value, right? You get states where the energy is minimum. If this is there, this has to be there because that's a symmetry related state. It comes from the symmetry of the problem. Okay. Now how do you understand this? Or what is the result? What does this result mean? This result means that if u is great, if this quantity is greater than 1, you will form a moment within the saddle point approximation. And how do you understand that? Look at this guy, right? As Sudeep was asking, there is a magnetic field here. That's this magnetic field. So if I put this to be a constant, it's like having a magnetic field. So the upspin will get a lower energy because it's pointing in the direction of the magnetic field. Let's say that you pick this saddle point, and the downspin will see a higher magnetic field. So what happens? This fellow will be here for the upspin, and the downspin fellow will be exactly symmetrically placed on the other side. It would be like this, right? And do you realize what these are? These are the Hubbard bands that you saw for this impurity, right? The Hubbard bands, right? That's what these are. Okay. Now, if this delta is very large, and this will be roughly u apart, right? If this delta is very large, this guy will come in a lot and mix with this, and then all the moment will go away, right? If delta is small, on the other hand, so something like this, then you can see that these two are fully separated out, and there is a fully formed moment here. Okay, and that's why this is the criterion. So this criterion of u pi by delta equal to 1 is a critical point in this theory. When u pi by 1 is less than, in this theory, in the saddle point theory, when u pi by delta is less than 1, you will see that there will be no moment, and when u pi by delta is greater than 1, you will see that there will be a moment. Okay? So this is the physics. So somebody was saying that we need large u, so that u should be able to hold on, and so the u should be large enough to protect against leakage. This is the leakage object. How much it hybridizes with the band. Okay, so this is the idea. Okay, now we know that this cannot be the full story. Why? Because if I pick this state, it's a symmetry broken state, it is not an eigenstate of the Hamiltonian. Why is it not an eigenstate of the Hamiltonian? Because there are processes by which, you see, I can have a quantum process in which I have this site. It's precisely the process that we discussed. I have this site. I'm saying that it is occupied by one up electron, right? But what can happen is that down electron can come here, pay an energy of u, and an up electron can go out. So what do I have? I have a spin flip process. I can have spin flip process. But if I have spin flip process, that will disturb this moment. Right? That will reduce the value of the moment. What is that process in this picture? In this picture, that process is the quantum tunneling between these two states. Right? So this is the classical potential, and I have to do the quantum fluctuations on this. So what do I have to do? I take the saddle point and I say, okay, my m of tau is not exactly constant, it is m of tau plus some fluctuating quantity. I put that in and I find the equations of motion for that fluctuation quantity, and you will find that it will hybridize these two states and get a low energy scale out of it. A low energy scale will emerge out of it, which is sort of related to this height. Right? Just remember this double barrier problem you solved. The effective transmission or the mixing coefficient will be exponentially related to that scale. Right? That's what you will get. And you will get this very nice thing called the Kondo scale. So if I were to just sort of think of this as some level, so there will be a hybridized level which will look something like e to the minus something like u by delta, this quantity. Something like this. You can see it's non-analytic, some square root u delta and all will show up. Okay? So this is the Kondo scale. So at the Kondo scale, what happens is that at large u, the moment is fully formed, but the moment can undergo spin flip processes. So it couples antiferromagnetically with the conduction electrons just around it. Why should it be antiferromagnetic? If the impurity spin is like this, if the conduction electron, which is that C dagger 0 to which it's hopping to, if it is opposite, then it can do the spin flip process. So it will pick up an exchange term which is actually proportional to, so there will be a J that appears which is actually proportional to gamma square by U in my notation. Right? Gamma is the kinetic energy, this is like T from the previous talk, and this is the U energy denominator, you will pick this up. So what you get, effective Hamiltonian will be the conduction electrons plus the antiferromagnetic interaction, this is called the SD term. So this will give you J spin of the conduction electron at the origin dotted with spin of my impurity. So this will be the effective Hamiltonian, right? And this J is related to this and so on. Okay. All right. Now we need some classical light. Yeah. J scale. Okay. And the effective Hamiltonian, once you get this J scale, would be just the conduction electrons. So this is called the HSD. So I have already written this. This plus some K, right? CK, C dagger K sigma, CK sigma. Okay, this is called the SD Hamiltonian. And what is this S0? S0 is the conduction electron spin density at the origin. At the origin of space. Because we put the impurity in space at the origin. Right? So this quantity is just this. Maybe some half etc. is there. Okay, we can put that. Okay, this is the origin of the physical space. Okay, that's what happens. Okay, now you see this is an antiferromagnetic interaction. Okay, so now let's say that I have J equal to 0 and I have a filled Fermi C. Okay, now the picture I'm going to draw has two things. There is both real space and K space in it. So you just need to be a little bit careful about that. Okay, so this is my Fermi C. Okay. And this is my physical origin also. I have this impurity spin sitting here. So what the impurity spin wants to do is, at the origin, at the origin of physical space, it wants to form a singlet with the conduction electron. But how can I form a singlet? To form a singlet, I need to localize particles near the because in the usual electron gas, the density is uniform. So if I want to form a singlet, I have to bring people around to that place, right? So for that I have to do some kinetic energy. I have to pay some kinetic energy. Is that correct? So what is the thing we will do? We will do the following. We'll take one electron from here and just put it outside. Right? So I have pushed out of this thing. So I picked up some k, and if I integrate over all possible states, then you can show that you will pick up some extra amplitude here, right, at the origin. And then what do? I do multiple particle hole excitations, and I can actually build up electron wave function here, and that electron wave function at that point will form a singlet with the impurity. Okay? So who is gaining and who is losing? The impurity, the J, the exchange interaction is gaining. And who is paying the price? The kinetic energy for localization here. Okay? And now you can show that this problem is precisely, at least mathematically, same as Cooper's pair formation problem. Precisely. The equations will be identical for one particle hole excitation. Okay? So I have, if you go to my web page, there is a set of notes called the Kondo effect. And if you just page down to this, there are nice pictures of this Kondo cloud and all that. So that what I just told you is the Kondo cloud. So the cloud just screens the impurity. And what happens is that you gain an energy which is sort of proportional to bandwidth times e to the minus 1 by j times density of states. So that's that. So that is actually related to this thing. So this is the only energy gained by forming the singlet. Exponentially small. But if you are at 0 temperature, that's infinite energy. Right? So at 0 temperature, this guy is just locked. The spin is completely locked to the conduction electron. You don't see any spin. It's totally locked to the conduction electron. It's form a singlet. There's no moment. There's no nothing. Okay? Now, as you start increasing temperature, what happens? Let's just make a plot here. Right? To form the singlet, all these wave functions must be nice and coherent and all, because you have to form linear combinations and the phases are related in some way and so on. Now, as I increase temperature, there will be incoherent particle hole excitations coming by increasing temperature. So what happens? This Kondo singlet wave function that is formed, it will start picking up random phase and it will start dying. Right? And when you go above this temperature scale, what happens? The conduction electrons are no longer able to screen the impurity and form a singlet, because anyway thermal fluctuations will kill this guy. Right? So what happens is there is a Tk scale. Here it forms by t equal to 0 it is fully quenched and slowly starts getting unquenched. And by the time you reach Tk scale, what has happened? You've completely sort of shown, you will see the moment appearing. And if you go higher and higher in temperature, the moment will be completely formed and will be completely free of the conduction electron band, because you go above J scale and all, nobody cares. The moment will be formed and it will just be free moment. Okay? So this is precisely what is called as asymptotic freedom. At high energies, it becomes a free theory. Right? So you have tightly bound object, you cannot see anything like quarks, tightly bound, and when you go to high energy, it reveals as individual particles. Right? Okay, so there is some very nice normalization group way of looking at it and so on, which I'm sure you will see in the thing. So what will happen is that there is a Tk scale, and I'll draw this U scale. So this U scale is where you will see that double hump. So you can take stuff from there and doubly occupy the, then you will actually lose the spin itself, because you will be able to thermally doubly occupy the impurity site. Right? And that was that experiment, that was shown and so on, where you can see the populating the upper band and so on. Okay? So there's a U scale. So this is the quenched moment regime. And this is the local moment regime. And this is a crossover, not a phase transition. It's a finite system. Okay? All right. So that's what I wanted to say. Okay. So you will see that this if I have a quenched moment in DMFT, it looks like a Fermi liquid and all that. So all those details you will see in the later set of talks. So the important thing is this mean field theory, which some gentleman was pointing out that we did. This is actually mean field theory, nothing more than that. The saddle point analysis, that is actually fake. Right? It actually doesn't capture the correct physics. So what I will do is I will close this discussion by reading out a line from Anderson's original paper, which I very strongly urge all of you to read. Right? It's extremely beautifully written. And okay. A final question is whether a real many-body theory would give answers radically different from Hartree-Fock results. Since our theory is exact in both limits, u equal to u going to 0 or u going to infinity, we expect only numerical modifications. Okay. In particular, the spin up and spin down electrons can probably correlate the times at which, there's some other stuff that's added. But this was the statement made in his paper, right? Of course, and then he of course changed that, and there was a series of papers by Anderson and Uval, which actually showed this, this process and showed that it's related to Coulomb gas and so on. It's extremely beautiful stuff. So there are some instant-on processes, like flipping from one to the other and kind of things. So they actually modeled that in some nice way and so on, and they showed that there is a Kondo scale that emerges and all that stuff. Okay, so let me stop here, and I will be around, and I will be around for a while because I live here, and you can always catch me and ask me any questions. Okay, thanks. Oh, thank you. Thanks a lot.